Hello again, Honors Chem students. Mr. Keister here with you for today, which is Friday, September 25th, 2020, which is our scheduled 26th day of school for the fall semester. Always keep in mind, though, the dates could change for a variety of reasons, but the lessons and the order of those lessons will remain the same regardless. So let's take a look at today's schedule, our do nows. Today you were to pick up Lab 2-1, real world gases. We're going to be getting to that here after we finish up our discussion on 2-1D that we started yesterday with the gas laws. You also are to pick up exam 2-1 review, which means we got an exam not too far away. That news will be coming here soon. So today we are going to finish up the gas law discussion today as homework. You'll continue working on yesterday's assignment, which was the Kinetic and Molecular Theory and Gas Laws Review, page 40. You were to do 1 through 11 for today. That answer key is posted on the board here and at home via my answer keys page on Canvas. But again, we didn't finish it yesterday, so you will be doing that today after I finish the lesson. That will be due Monday by the beginning of class. I will be collecting it for a grade. All right, so the assignment you started yesterday, you are to finish for Monday. I will be collecting it for a grade. When I finish the discussion over 2-1D, you're to go back in the lab area and begin working on Lab 2-1. We will be doing that here shortly. I'll be doing that with you. Rotate around the lab stations and be sure to answer the questions completely on your lab paper. That lab is also due Monday by the end of class, And I'll be collecting it for a grade as well. So the assignment from yesterday will be due at the beginning of class. The lab will not be due until the end of class. So you have some time to converse with your lab partners, get your story straight, and make sure that your lab papers are filled out completely. FYI, exam 2-1 will be coming on Tuesday, all right? I posted the study list in Canvas today, and it will be on the board Monday. Be working on your exam 2-1 review, which you picked up today. It's technically due Monday by the end of the period, but of course I won't be collecting it until exam day on Tuesday, which is normal protocol. All right, so having said all that, let's get back to where we were from yesterday and finish that up. Okay, let's bring up the page. So we are continuing on. I think we covered Boyle's law, Charles' law, and Avogadro's law, one version of it anyway, yesterday. Today we're going to look at the fourth and final gas law, which is Gay-Lussac's law. So let's look at that. So we're looking now at example 4. So the air pressure in your automobile tires is 2.59 atm. So there's pressure 1. At 25 Celsius, what do we say about gas behavior and temperature? Remember, it is dependent upon Kelvin temperature. I can't say this enough. You must convert your Celsius temperatures to Kelvin in order to get the correct ratio of new temperature to original temperature. So T1 plus 273 would give us 298 K for T1. All right, 298 K. You drive your car up to the top of a mountain where the temperature is 10.0 degrees. So T2 then plus 273 would be 283 K. So the temperatures drop. What is the new pressure in the tire? So we're looking for P2. All right, so we have P1 is 2.59 ATMs. Again, make sure you label these correctly. T1 in Kelvin is 298 K. Temperature 2 is 283 K. And we are looking for P2. Volume and number of particles is constant. Okay? So, the effect on temperature is that it decreased. As temperature decreases, collision rate decreases, which then means pressure does what? It, of course, decreases as well. It is another direct relationship. Whose is it? As we said a little bit ago, this is Joseph Louis Gay-Lussac's law. That says pressure and Kelvin temperature are directly proportional. So let's do the math dimensionally, and then we'll derive the equation, which hopefully by today shouldn't be too much of a surprise. So we start with our 2.59 ATMs, put it over 1. We are going to use our temperatures as a conversion factor. Those both in Kelvin, of course the Kelvins cancel. We want our pressure to go down since the temperature went down. So how are we going to place those numbers, those two numbers, so that the pressure goes down? Hopefully you say that the smaller one would go on top, which is true. 283 divided by 298 is a number less than 1. You multiply 2.59 by a number less than 1, you get a smaller volume, or smaller pressure, which is what we want. So we do the math. Our original measurement in ATMs was 3 sig figs. 2.46 ATMs is our answer. All right, 2.46. Let's look at particle diagrams. So initially, we have, let's just say 2 particles. How about the volume? Did the volume change? No. So our final box should look the same size, still 2 particles. Did the temperature change? Yes, it did. It went down, which means the speed goes down. So I'm going to give 2 bars of speed initially and only 1 bar of speed in the final scenario. And again, with a decrease in temperature and a decrease in collision rate, the pressure is going to go down. So I'm just going to give the final ones 1 collision, but I'm going to give the initial ones 2. Okay? And there we go. All right, so let's derive the equation for Gay-Lussac's law. So we started with P1 over 1, and we multiplied it by T2 over T1, and that then gave us, I guess I should have said P2 there, and that gave us P2. So again, do a little algebraic rearranging here. I'm going to multiply both sides, got to look here, by 1 over T2. Times 1 over T2 times 1 over T2. The T2s on the left cancel. The 1s, of course, we can disregard. So we end up with P1 over T1 equals P2 over T2. Again, with a direct relationship, this equation format should not surprise you, all right? The ratio of the 2 is a constant. That's what a direct relationship says. And so this is the derived equation for Gay-Lussac's law. Okay, right there. All right, so let's run the numbers with the equation. So P1 is 2.59, T1 298 equals P2 we're looking for, and T2 was 283. Of course, this being a proportion, we will cross multiply, divide. 298 times P2 equal 2.59 times 283. Divide both sides by 298. No surprise, that's what we did over here. And P2 then, to all our data now, this P of sig figs is 3, so we're still at 3 sig figs. 2.46 ATM. No big shock there. All right, so again, whichever method you choose to do your math, dimensionally or via equation, that's fine. Just make sure you show all the work that is required for either one of those methods. And of course, label and round properly as well. Question there. So we've hit Boyle's, which is inverse, pressure and volume inversely related. We've hit Charles, volume and temperature, volume and Kelvin temperature directly proportional. We've hit Avogadro's, pressure and number of particles directly proportional. Remember, the other version of Avogadro, if you have a flexible container, is volume and number of particles directly proportional. And then here, Gay-Lussac's, pressure and Kelvin temperature directly proportional. All right, so we've hit them all. Let's do one that involves a combination of several factors. I'll show you that. It works the exact same way. All right, so let's scoot this up. There we go. Your bike tires each contain 15 units of air particles. So there's N1, and each has a volume of 168 ml. There's V1. Under these conditions, the pressure reading is 17.0 psi. There's P1. Another factor now. One of the tires develops a leak. It now contains 12 units of air particles. There's N2. And is contracted to a volume of 154 mLs. There's V2. What is the new air pressure in the tire? We're looking for P2. All right, so we got some additional numbers to work with here. Let's throw them all in the PD&T chart. All right, so N1 was 15.0 units of particles. V1, 168 mLs. P1, 17.0 pounds per square inch, PSI. N2, 12.0 units of air particles. I had this happen to me the other day, unfortunately. Yeah, I had to stop and put air in my tire at like 3:30 in the morning. That was fun, finding a place to do that. Okay, volume 2 was 154 mLs. We're looking for P2. The temperature remained constant. All right, so we have several factors working here on this pressure now, not just one. We got to take into account both of them. So let's start with our volume. So our volume went down. We'll call that our first factor. And our number of particles went down. We'll call that our second factor. Again, both of those factors are working on the pressure. So let's look at them individually. With a decrease in volume, what happens to pressure? Remember, this is Boyle's. So with a decrease in volume, the particles are closer together. They're going to collide more often. Pressure goes up. So our first effect on pressure is that it goes up. That's from the decrease in volume. Now, the second factor is the number of particles goes down. With a decrease in number of particles, the pressure is going to go down. All right, that's Avogadro's law. All right, so the pressure then, as a result of the reduction in air particles, goes down. So we have two effects, one from each set of factors. All right, so this is Boyle's and Avogadro's law. Both of them. All right. This is in effect a combination or a combined gas law where multiple factors are involved. Okay. We actually have a term we actually use that term combined gas law when we're talking about changes in volume, pressure, and temperature. All right. That is actually called the combined gas law. This is also a combined gas law, but it's not really the combined gas law. All right. But we have multiple ones of those. All right, so let's do the math dimensionally. So we're going to start with 17.0 psi's, put it over 1. We now have two factors, all right? Our first factor involved the volumes change. Our second factor involved the units change, the number of particles. Again, all those units are going to cancel. We're still going to get with psi for our final answer. Well, now let's look here. So we said with a change in volume, the pressure goes up, up. So how do we use these two numbers? We want an increase in pressure, so the larger one's got to go on top, 168 over 154. Second factor, the units went down, the number of units went down, which makes the pressure go down. So now we need the smaller unit on top. Same rationale as before. If we want a factor to go up, we put the larger number on top in our conversion factor. If we want it to go down, we put the smaller one on top. Same principle. All right. So now we got 17.0 times 168 times 12.0 divided by the product of 154 times 15.0. Just got a few extra numbers to deal with. Original measurement, 3 sig figs. And so answer 3 sig figs, and we get 14.8 psi. So what happened to the pressure? It went down. Now remember, the change in volume would have forced the pressure to go up, but the change in number of particles caused the pressure to go down. Overall, it did go down. So which was the overriding factor? The change in volume or the change in the number of particles? And I hope you can see that in this case, it is the change in the number of particles that was the deciding factor, since the pressure went down. Okay, hopefully you got that. All right, let's derive a bigger equation, shall we? All right, so we started with P1 over 1. We multiplied that by V1 over V2. And we multiplied that by N2 over N1. And what did it give us? It gave us P2. Got more algebraic hocus pocus to do here. All right. So let's see. What did I do here? Well, the first thing I did, actually, I'm do it all at once. I took both sides and multiplied them by B2 over N2. All right, B2 over N2. So times B2 over N2 times B2 over N2. Now, why did I do that? Well, let's look. These N2s cancel, and these B2s cancel. And what do we end up with? We end up with P1 times B1 over N1 equals P2 times B2 over N2. Let's take a look at that, all right? So this is a combination of two gas laws, or a combined gas law. So look, P1 times B1 equals P2 times B2. That's Boyle's law, volume and pressure inverse. There she is, all right? Then we have Avogadro's law, P1 over N1, P and N equals P2 over N2. Direct relationship, Avogadro, there it is. Both laws are there in one derived equation. Now, you may not want to go to the trouble of doing all that, or you may not want to go to the trouble of having to remember that equation. Doesn't matter. You can do the math that way, or you can do the math dimensionally. Maybe on these combined ones, it's easier to do it dimensionally. I don't know. It's up to you. Again, I don't care what you do, but as long as you show what you're supposed to show. I'll go ahead and do the math this way, and we'll see what we get. So P1, 17.0 times B1, which was 168, over N1, which was 15.0, equals P2, don't know that one, B2, 154, and N2, 12.0. So we just have a bigger proportion, got a couple of extra numbers, all right? We're still going to cross multiply and divide. So we have 15.0 times 154 times P2 equals 17.0 times 168 times 12.0. So we're going to divide both sides by the product of 15.0 times 154, which is 2,310. Divide both sides by that. And our original measurement, 3 sig figs, so this one would too. And lo and behold, P2 is 14.8 SI. Same answer. All right, let's do a particle diagram here and we'll put this thing to bed. So looks like we start with the initial. Now, the volume went down, so we need to make sure that our final box is what? Should be a little smaller. So make sure we show that. Did the number of particles change? Yes, it did. It went down. So I'm going to simply show 3 here versus 2 here. Did the temperature change? No. So the speed's the same. So I'll give them 1 bar of speed either way. And what happened to the pressure? It went down. Well, we're showing, so I'll give them all a collision. Are we showing that? Here we're showing 3 collisions. Here we're showing 2. Did the pressure go down? Yeah, and we said the overriding factor was the pressure went down because the number of particles went down. That was the overriding factor in this scenario here. So I think we're good. So there we go. All right, so your assignment is to finish the assignment. This is assignment for Monday. You are to finish the assignment that you began yesterday. Now, let's head back to the lab and look at lab 2-1. If time in class runs short for you to finish lab 2-1, remember Monday is actually a work day, and I said the lab isn't due until the end of the class on Monday. So if hopefully you can get through all the demos today, but if for some reason you don't, I'll leave them set up for Monday and you can finish them then. And then, of course, get with your lab partners and get all the rest of the stuff written down that you need to do before the end of the period. So, having said that, let's go back to the period. Okay. Now I'm going to have to move the my laptop around here a little bit as we do the various experiments. So for now, I'll set it right up here and point it down again. It might be cutting my head off at times. So we'll see there how that works out. Hopefully it'll be okay. Okay, so now we got lab 2-1, all right, real world gases. So for each activity, you're to record your observations, determine which variables, pressure, volume, temperature, and number of particles, remember PV, N, or T, are involved and what the relationship is, direct or inverse, between the variables. Draw particle diagrams to explain your observation that illustrate your explanation of what happened at the particle level. Identify whose law is involved and write the equation that we derived for it. So activity A, in an empty dry syringe is placed a marshmallow. The plunger is set in place and pulled about halfway up the syringe. Cap on the end of the syringe seals it. Experiment with pulling the plunger in and out. So here it is. So notice in there, there's a marshmallow. It's actually a green one. All right. There is air in there. All right. So if I push the plunger in, what's happening to the volume of space in that plunger there? Well, it's decreasing. So, all right. So if the volume is decreasing, we're not changing temperature. We're not changing number of particles. We're just compressing those air particles into a smaller space. So what's going to change is the pressure. All right. So let's do it. So let's see. There we go. Oh, look. The marshmallow, I hope you can see it, is crumpling up. It's getting tinier. It's little. All right. We placed a great amount of pressure on that marshmallow. It's squishing it. So now as I increase the volume, oh, look at it now. As I increase the volume, that marshmallow is getting bigger. All right. Smaller. Bigger. Okay. So the marshmallow shrinks when the plunger is pushed in, and it expands when the plunger is pulled back. Okay, this is a result of a change in pressure, which comes from the change in the volume within that plunger. So volume and pressure are our variables. So you are to write down the relationship between pressure and volume. You should know it. And whose gas law that is? Whose is it? I'll help you with this. It's Boyle's law. All right. V is inversely proportional to P, or P is inversely proportional to V is the relationship. The equation for Boyle's law we derived is V1 times P1 equals V2 times P2. So now you are to draw particle diagrams, both initial and final, for when we push the plunger in, which means the volume is decreased, and of course the pressure then would increase. And then a second set of particle diagrams, initial and final, for when the plunger is pulled out. When you pull the plunger out, the volume increases, and then, of course, the pressure decreases. So that's the first one. Put that over there. Second one. All right. Let's see here. I may have to move this down. Here. No, I can't see it too much. Let's do it this way. There we go. There we go. That's better. Okay. I'll get down here. All right. So in the second one, we have a soda bottle, which is flexible, as you can see. Now look carefully. Right in there. See that thing in there floating around? There it is. There it is. Right there. There's an upside down test tube in there, and it's got some air trapped in it, so it's floating. All right, it's floating. It's floating upside down. So what I'm going to do is squeeze tightly and then release the sides of the soda bottle and watch what the inverted test tube does. All right. So looky here. So I'm going to squeeze the bottle. Now watch. Uh-oh. There she goes. Test tube sank. And as I release the pressure I'm placing on the bottom, there it comes back up. Down she goes. Up she comes. All right. What's going on there? Well, what's happening? Have we changed the temperature? No. Have we changed the number of particles in there? No. So here again, once again, it looks like we're changing volume and pressure. All right. As I squeeze the bottle and the volume inside decreases, the volume of air decreases. All right. The pressure increases. That pressure increase pushes more water inside that upside down test tube. And when it pushes more water in there, it sinks. Okay. When I release the pressure and the volume of air increases, there is now more air in the test tube, which decreases its density in there. And of course, the test tube then flows. So once again, our variables are P and V, same as in the letter A. Remember that relationship we just discussed. So now I want you to draw two sets of particle diagrams. First, when you squeeze the bottle, of course. So you start off with a certain volume. When you squeeze the bottle, the volume decreases. So the pressure goes up. Draw a set of particle diagrams there, initial and final. And then draw a second set. When I release the bottle, all right, now the volume is increased, and so the pressure has decreased, and so more air goes in the tube, and up it comes. So when I release the bottle, the volume has gone up. Make sure you show that in your diagram, which means then the pressure would go down. Okay? All right, up we go. Third one. So now we're on the back of the page. Oh, this is a good one. I love this one. All right. So here I have a little container of, I put colored water in it so you can see it better. All right. And I've got a jar here. Hello, everyone. I've got a jar here, and I'm going to put this, I'm going to light the candle first. All right. And then I'm going to put the jar in there and cover it up, which is going to cut off its air supply. All right. So what do you think is going to happen to the candle eventually after it uses up all the air in there to burn that wick? Well, if you say it's probably going to go out, you're right. All right. But let's see what happens when that happens. So I'm going to light the candle. hopefully. There we go. Now I've got a little stick in here that you can see. I want to make sure that I set the inverted jar. Of course, it's got a lot of air in there, right? A lot of air in that jar. I want to make sure that it's sitting on the stick, all right, so that it doesn't seal it, okay? I want you to see what happens. So let's put her in there. There we go. So now look inside the inverted flask. There's some colored water in there. So the flame's burning. It's getting a lot. Oh, uh-oh. There goes the flame. Now watch. Oh my goodness. Did you see that? The water level in that upside down flask just shot up. Went up about that much. All right? Went up about that much. What in the heck happened in there? All right? Well, let's talk about it. Gosh, it's hard to get up off my knees nowadays. Sheesh. All right. So what are we changing now as the candle burns and finally goes out on its own? Well, we're changing the number of air particles inside that jar, all right? So the number of particles is decreasing, all right? So what's changing in that flask as a result of the number of air particles decreasing, all right? Well, we're changing the pressure. If you have fewer particles, remember the pressure is going to go down. Whose law is that? Direct relationship between number of particles and pressure. I'll leave that up to you, all right? So the variables are N and P. Relationship we looked at, we saw it's direct. Whose law is that? What's the equation for it? I'll leave that up to you. So again, what happened? We light the candle. Air particles are used up. And so once that happens, the pressure decreases. So now there's a greater pressure outside that flask than there is inside, and it pushes the water in. Okay, pushes the water in. Kind of like a change in pressure when you suck on a straw is when you don't. Same thing, same exact thing. Make sure you draw an initial and final particle diagram showing a decrease in number of particles and pressure. The volume is constant. As you can see, the flask is the same size. It's a rigid container. All right. So let's go on to the next one. I like that one. All right, so let's see here. How do I want to place this? I want to place it, well, we'll see. I'm going to fiddle around with this a little bit. Let's see how it goes here. Scoot that there. All right, so here's what I want you to see here. For reference, I have 3 balloons, same size, all right? Now, I just use this as a comparison, this one here. So this, there are 3 same size balloons. I just blew like one little breath of air in them, and then I sealed them over the top of the Erlenmeyer flask. So hopefully, within reason, of course there's air involved, but within reason, we've got the same volume of air in each one, all right? So we'll assume the number of particles of air, actually CO2 is what I blew in there. We'll assume that those are the same. So this is our reference. So you see what the balloon looks like. Definitely got some air in it. And that air is at room temperature. All right. So that was our kind of our reference. Now look at now I've got this balloon, same size, started out the same as this one, that is now in a cold ice water bath. Look at the difference. Look how much flatter it is. Did air leak out? No, didn't leak out. The balloon's still sealed. What happened to it though? As the temperature of the air inside that balloon, or the CO2, inside that balloon went down, since this is a flexible container, those particles slowed down, the collision rate was less, and so the volume of the balloon decreased. All right. Over here, a little different. I've got this balloon now on an Erlenmeyer flask that's been in a hot water bath. And I want you to see now, look here, how this balloon has expanded, all right? It's got the same amount of CO2 in it or air in it that the other two have. But with an increase in temperature, hi, I'm back. So with an increase in temperature now, those particles in there are speeding up and increasing their collision rate. Since the container is flexible, it's getting larger. All right. So now our variables are, the number of particles is the same. All right. But our variables are temperature and volume, since we have a flexible container. A balloon is a flexible container. All right. So our variables are volume and temperature. So the observations was the cold balloon shrinks and the hot balloon expands. Okay. So we have a relationship between volume and temperature, the direct relationship. Who is it? I'll leave that up to you and the accompanying law. So I want you to draw two sets of particle diagrams. The first one, our initial volume is the room temperature balloon, all right? And our final volume is the contracted or shrunken volume of the cold balloon. The second particle diagram, again, starts off with the room temperature balloon as your initial particle diagram, and then your final particle diagram is the one that has been heated, all right? So we've got room temperature to cold and room temperature to hot would be our two sets of initial and final particle diagrams. So that takes care of that one. All right, let's look at the last one. All right, so let me move this out of the way here. Scoot that over there. And we'll scoot this over here. And okay. Do I want to do it like this? Let's see. Oh, that works. That'll work. Okay. So, as you can see, I have two little containers here and lids. So now these are fixed volume or rigid containers. All right. So volume's not going to be a factor in this one. So this is part E. The active ingredients in Alka-Seltzer tablets, or the active ingredient is sodium bicarbonate, which produces carbon dioxide gas when it's mixed with water. So this, when you take an Alka-Seltzer tablet, okay, what does it cause you to do? Well, it produces CO2 gas and you start burping, which is hopefully to relieve the extra pressure that's in your stomach that's causing you to have heartburn or a stomach ache. That's the whole idea behind that. So we're going to fill a film canister about half full with water. So I'll do that to both of them while we're at it. Let's see. Looks about right. And try to get about the same in the other one. That looks pretty good. Okay. All right. Oops, my boiling water over here is talking to me. I'll go ahead and cut it down now. There we go. Now I'm back. All right. So place a quarter of an Alka-Seltzer tablet in the film canister and quickly put the lid on. Okay, so here's my quarter of a tablet. So remember, when we put the tablet in water, we're going to get a chemical reaction. It's going to produce CO2 gas. All right, it's going to produce CO2 gas particles. Let's see what happens. Seal it. Come on now. What it? Love it when that happens. All right. So what's going on now? What's happening in there? Well, we're producing a gas. So now we're increasing the pressure inside the container because we've added gas particles. And what I hoped to have happened was that the increase in pressure would be enough to pop the lid off. Doesn't seem to be doing that. Let's see if we can hear a gas when I release the lid. Well, yeah, I want you to see there's bubbles, gas bubbles forming in there. But apparently the pressure increase just wasn't enough to pop the lid. So for that, I failed. Sorry about that. So let's try it again with a larger tablet. Of course, with the larger tablet, there's going to be more mass of our original ingredient here, sodium bicarbonate. So it should produce more CO2, all right? So more gas particles. So let's see if we can get this one to work. Guess I should have tested this before. I have a feeling the Alka-Seltzer tablets, which are from last year, perhaps have degraded somewhat. So we'll see. Tell you what I'm going to do. Get a new tablet. I got time. Try it again. See if that has anything to do with it. Oh, goodness! Ha! That surprised me, and I just spilled the water. Oh, well. Anyway, a little delayed reaction there, but I guess now I don't need the other tablet. So, see all the bubbles in there? Lots more than in the first one. Love it when unexpected things happen. Well, I expected something to happen, then it didn't, so I gave up on it a little too early, and then it did happen. And like I said, I spilled water out of this canister all over the floor. Oh, well. That's Mr. Keister for you. Adding stupid stuff all the time. So what's our observation? So the gas produced, so we have a fixed volume container. So the gas produced in there, so we increase the number of gas particles, which increases what? Increases the pressure in there. As we finally saw on the second one, the pressure was great enough to pop that lid off. So the gas produced increases the pressure inside the container, and then, of course, hopefully pops the lid off. The one didn't, but the one did. So our variables now are N, number of particles, and P, pressure. And as you can see, they are directly proportional. Whose law is that? All right. And how does that law read? Okay. So now I want you to draw an initial and final particle diagram whereby now the volume's constant. So the boxes should be the same size. But now we've increased the number of gas particles in the canister from initial to final conditions. And of course, as a result of that, we will get an increase in pressure. So those are the 5 activities in Lab 2-1. Again, in class, if you are in class and actually do this yourself, hopefully you will be. If we run out of time, no problem. Then we'll save time for the next day, which is a work day, Monday, so that you have time to finish it and to get everything written down with your lab partners in order to turn it in by the end of class. But your assignment that we started yesterday, that is due at the beginning of class on Monday. So until next time, this is Mr. Keister signing off. Take care, everyone. Keep working hard. I'll see you Monday. Stay safe until then. Take care. So long, everybody.